Right, so full duplex, power save, auto negotiation, and 802.1x flow control. When Ethernet was first developed, it operated only in half duplex mode using a shared cable. That is, data could be sent only one way at one time, so only one station was sending a frame at any given point in time. So that was half duplex. You cannot send back asynchronously. With the development of switch Ethernet, the network was no longer a single piece of shared wire, but instead many sets of links. As a result, multiple pairs of stations could exchange data simultaneously or asynchronously. In addition, Ethernet was modified to operate in full duplex, effectively disabling the collision detection circuitry. So, in the previous video, we discussed the collision detection circuitry, in which you are not allowed to hit a certain length with the half duplex, because from that point it will not be worth it when some packet were lost. In this case, it was converted to a full duplex that allow asynchronous communication. That's also the reason why your cable could just be one cable, but could have different LANs and different packets sent into it. This also allowed the physical length of the Ethernet to be extended, because the timing constraints associated with half duplex operation and collision detection were removed. So because the constraints in length to avoid packet loss were only prevalent with the half duplex, now we don't have that constraint, so we have longer Ethernet cable for full duplex. In Linux, ETH tool program can be used to query whether full duplex is supported and whether it is being used. So here's the command: ETH ETH0, supported ports TP MII, supported link modes 10 base T slash half, 10 base T slash full. The speed is 10 millibytes per second. Duplex half, so it means it's a half duplex. Port MII, FIAD or physical address 24, transceiver internal, auto negotiation on, current message level 0x and 601. Link detected, yes, so that means it is being used. ETH tool ETH1, let's see, supported ports TP, again supported link modes 10 base T slash half, 10 base T slash full, 10 base T slash half, 10 base T slash full, 100 base T slash full. Speed 100 MB per seconds. Duplex full, so it's a full duplex. Port twisted pair, FIAD 0, transceiver internal, auto negotiation on, supports wake on UMBG, so we will discuss this UMBG later. Wake on G, so when this G parameter uh, has been applied, this Ethernet will on. Current message level 0x707. Link detected, yes, so it means it's currently using. In this example, the first Ethernet interface ETH0 is attached to a half duplex 10 MB per seconds network. We can see that it's capable of auto negotiation, which is a mechanism originating with 802.3U to enable interfaces to exchange information such as speed and capabilities, such as half or full duplex operation. So this actually stems from 802.3A standard to enable interfaces to exchange information such as the speed and capabilities. So this auto negotiation is a mechanism that enable these interfaces to share information such as its type of duplex and its speed. Auto negotiation information is exchanged at the physical layer using signals sent when data is not being transmitted or received. So if the data is not being sent or received or being transmitted or received, this auto negotiation at the physical layers use signal to exchange this data. We can see that the second Ethernet interface ETH1 also supports auto negotiation and has set its rate to 100 millibytes per second and operation mode to full duplex. The other values, port, phi add, transceiver, identify the physical port type. Its address and whether the physical layer circuitry is internal or external to the NIC or NIC. So as we can see, we have the port type TP and the phi add its address or the physical address and whether the physical layer circuitry is internal or external to the NIC. So this port could be external from its actual NIC or internal, meaning within the machine. So that's what transceiver means. Transceiver, it means that this machine and the INC is incorporated inside. The current message level value is used to configure log messages associated with operating modes of the interface. So this value are what you will use to configure log message associated with this with operating modes of this port. Its behavior is specific to the driver being used. So this current message modes, you can use this or configure this depending on the driver being used by this port. We discussed the weak on values after the following example. So the weak of on values is kind of a different feature. I mean, it's kind of related as well, but here we start with Windows 7. In Windows, details such as these are available by navigating to Control Panel, Network Connection, then right-clicking on the interface of interest, selecting Properties, and then clicking Configure box and selecting the configure box and selecting the advanced tab. This brings up a menu similar to the one shown in this 3.6. This particular example is from an Ethernet interface on a Windows 7 machine. So if we navigate to Control Panel, let's do that now. Control Panel, Network Connections, Network and Internet, and right clicking on the interface of interest. So as of now, I don't have networking device that shows on my control panel, but I would assume that I would need to right click the interface and then selecting its properties and then clicking configure box, and I will select the advanced tab to be able to this to go to this. So that's, I guess, how I would be able to configure it. Let me check again. I think I have a network hardware here. Yeah, I don't actually have other network here. So I would assume that if I am connected to a network, I can right click that and then configure it to be like this. So here is the advanced tab of network interface properties in Windows 7. This control allow the user to supply operating parameters to the network device driver. So we can set it to 100 MB. So this will be used by the network driver to configure this then log depending on the port or the interface that we are configuring. We can set it to auto negotiation 100 Mbps, half duplex 100 Mbps, because as you can see in the ETH1, it support those link modes, and then auto negotiation is on. Okay, I see. So in figure 3.6, we can see the special features that can be configured using the adapter's device driver. For this particular adapter and driver, 802.1p/q tags can be enabled or disabled. So the tags we discussed earlier, where we add the VLAN ID and the priority, can be actually configured here, can be enabled and disabled. As can flow control and wake up capabilities. So when we click this, the driver, I guess, I think it's in device manager now. Let me just check this. Network. I see network adapters. I see, yeah, it's in the, when I click the properties, yeah, I see it's in the network, general details, power management. Yes, it's in the device manager now in Windows 11. So I have IPv6 properties. So I do not have where's the advanced? Just a moment. Driver details, events. Let's check the Intel. I see. So I have here I don't know if I can still add this while recording. Let's see. Display capture. Let's do this. Yeah, guys, I hope you can see. So here's the advanced that I used to that we can use to configure dual band, A/G, etc. ARP. So I get that in the device driver. I guess I can delete that now. Let's just delete this. Yeah, so basically in the driver's side, we can enable or disable that. So that's for Intel, the P/Q tag. So we can disable that there. As can flow control and wake up capabilities. So the flow control, which we'll discuss later, and the wake up capabilities. The speed and duplex can be set by hand or to a more typical auto negotiation option. So the more typical configuration here is the auto negotiation, because again that auto negotiation is also what allow us to provide or exchange those information. Duplex mismatch, historically there have been some interoperability problems using auto negotiation, especially when a computer and its associated switch port are configured using different duplex configuration, or when auto negotiation is disabled at one end of the link but not the other. So there is an issue if the auto negotiation is disabled from another port that the host are connecting to. In this case, a so-called duplex mismatch can occur. Perhaps surprisingly, when this happens, the connection does not completely fall, but instead may suffer significant performance degradation. When the network has moderate to heavy traffic in both directions during large data transfer, a half-duplex interface can detect incoming traffic as collision, triggering the exponential back-off function of the CSMA/CD Ethernet MAC. So, if the one port has half duplex and it receive a heavy traffic in both direction, it will trigger the old issue of CSMA/CD, or the exponential backoff function. So of CSMA/CD Ethernet MAC. At the same time, the data triggering the collision is lost and may require. So at the same time, the data that triggers this collision, or the last data that is in the queue, is lost and may require higher level of protocols such as TCP to retransmit. So you'll be needing to configure this in the TCP or higher level to be able to retransmit it. Thus, the performance degradation may be noticed only when there is sufficient traffic for the half-duplex interface to be receiving data at the same time it is sending. So, but it only happens if the half-duplex interface are receiving data at the same time it is sending. So, a situation that does not generally occur under light load. Wake on LAN, power saving and magic packets. So this is where the wake online that we can configure in the driver as and the flow control. So we're gonna discuss flow control later. In both Linux and Windows example, we saw some indication of power management capabilities. In Windows, the wake up capabilities, and in the Linux, the wake on options are used to bring network interface or host computer out of a lower power sleep state based on the arrival of certain kinds of packets. So you can configure a certain type of packet to wake up that interface or port. That's what wake on LAN means. In Linux, the wake on values are 0 or more bits, indicating whether receive receiving the following types of frames trigger a wake up from a lower power state. And physical layer activity. So these 0 or more bits are VHY. VHY. So if it receives frames from any physical layer or from any activity, unique or from unicast frames destined for the station U, multicast frames M, broadcast frames B, ARP frames A, magic packet frames G, and magic packet frames including a password. This command configures the ATH0 device to signal a wake up if any of the frames corresponding to the types U, M, G, or B is received. So ATH tool -S ATH0 wall UMGB. When Windows provide a similar capability, but the standard user interface allows only magic packet frames and a predefined subset of the U, M, B, and A frame types. Windows provides a similar capability, but the standard user interface only allows only magic packet frames and a predefined subset of UMB and frame types. So it's not as configurable as Linux because it only allow magic packet frames and a predefined subset of the UMB and frame types. Magic packets contain a special repeated pattern of the value 0xFF. Often, such frames are sent as form of UDP packet. So magic packet are often sent as form of UDP packet. So see chapter 10, encapsulated in a broadcast Ethernet frame. Several tools are available to generate them, including WAL. So here, Linux WAL 200:08:734:93:C8:3C. Now it will wake up that. So the result of this command is to construct a magic packet, which we can view using Wireshark. So here's an example of that in Wireshark. The packet shown in figure 3.7, a magic packet frame in Wireshark begins with 60xFF bytes and then repeats the MAC address 16 times. So here the sync stream FFFFFFFF and then this 16 times. So that's the magic packet frame in Wireshark. The packet shown in figure 3.7 is mostly a conventional UDP packet, as we can see here, user datagram protocol. Although the port numbers 1126 and 40,000 are arbitrary, the most unusual, so arbitrary meaning there's random, the most unusual part of the packet is the data area. It contains an initial 6 bytes with the value 0xFF. So as you can see, we have 0x2FF here. The rest of the data area includes the destination MAC address 00087493C8 repeated 16 times. These data payload patterns define the magic packet link layer control flow. Operating an extended Ethernet LAN in full duplex mode and across segments of different speed may require the switches to buffer store frames for some period of time. So if you're using full duplex, which is most modern ports nowadays, across segments of different speed, it may require the switches to buffer or store frames in its database. This happens, for example, when multiple stations send to the same destination called output port contention. So if a lot of stations send to one or same destination, we would encounter this. If the aggregate traffic rate headed for a station exceed the station's link rate, so the maximum session it can connect to, frames start to be stored in the intermediate switches or the switches near it. If the situation persists for a long time, frames may be dropped. One way to mitigate this situation is to apply flow control to senders, meaning slow them down. Some Ethernet switches and interfaces implement flow control by sending special signal frames between switches and NICs. So it will send a special signal frame between the switches and that port that is requesting. So that's actually one of the capabilities we could implement on driver part in Windows 7 earlier. Flow control signals to the sender that it must slow down its transmission rate, although the specification leaves the detail of this to the implementation. Ethernet uses an implementation of flow control called pause messages. So this is the implementation that is left with the user of this with the user of this special control signals called pause message, also called pause frames. Pause message is the frame, the type of frame being sent, specified by 802.3x 802.3 to 2008. Pause messages are contained in MAC control frames identified by the Ethernet length or type field having the value 0x88088 and using the MAC control opcode of 0x0001. So instead of the envelope frame, it has an additional or what we call MAC control frame. So it is stored in MAC control frame with an additional MAC control opcode of 0x0001. And also it is identified by the length or type field having the value 0x8808. A receiving station seeing this is advised to slow its rate. Pause frames are always sent to the MAC address 01 colon 80 colon C2 colon 00 colon 00 colon 01 and are used only on full duplex links. So there is a special MAC address that these IEEE standards allow to send it to. So it's not really being sent, it's meant to use for the receiver to read it to be able to slow its rate. So they include a hold off time specified in quantas equal to 512 bit times, indicating how long the sender should pause before continuing to transmit. The MAC control frame is a frame format using the regular encapsulation from envelope frame but with a 2-byte opcode immediately following the length or type field. So that's the opcode 0x0001 following the 0x8808 after the length or type field. Pause frames are essentially the only type of frames that uses MAC control frames. So these are the only frames that use MAC control frames. They include a 2-byte quantity encoding the hold off time. Implementation of the entire MAC control layer, basically just 802.3x flow control, is optional. So this is optional. Using Ethernet layer flow control may have a significant negative side effect, and for this reason it is typically not used. When multiple stations are sending through a switch that is becoming overloaded, the switch may naturally send pause frames to all hosts. So if the switch are being overloaded, if it's turned on, it will naturally send pause frame to all hosts. Unfortunately, the utilization of the switch memory may not be symmetric with respect to the sending host. Unfortunately, the synchronization or the configuration of the switch memory may not align with the host or the behavior of the host, because that's unpredictable. So some may be penalized, flow controlled, even though they were not responsible for much of the traffic passing through the switch. Now we discuss bridges and switches. The IEEE 802.1d standard specifies the operation of bridges and thus switches, which are essentially high performance bridges. So a switch are essentially just high performance bridges. A bridge or switch is used to join multiple physical layer networks, a pair of physical Ethernet segments, or group of stations. So a pair of physical Ethernet segments, like this. It has two stations and it has two stations on the other side. The most basic setup involves connecting two switches to form an extended LAN, as shown in Figure 3.8. Figure 3.8, a simple extended Ethernet LAN with two switches. Each switch port has a number for reference, and each station, including each switch, has its own MAC address. So as you can see, the switch has a MAC address, not just the station, because again, in TCP or IP, a switch could function as its own, but it could be a host as well, just like the Windows host that we discussed, that allow to configure or to connect multiple bridge, or to configure the network interface. Switches A and B in the figure have been interconnected to form an extended LAN. In this particular example, client systems are connected to A and servers to B, and ports are numbered for reference. So in this case, the server are connected to B and A connected to switch A, or the client are connected to switch A. Note that every network element, including each switch, has its own MAC address. Non-local MAC addresses are learned by each bridge over time, so that eventually every switch knows the port upon which every station can be reached. So this is the standard feature of a switch or a bridge. It learns that over time. So when you configure multiple network interface on your host or operating system nowadays, it will have that basic feature of a switch. So these lists are stored in tables called filtering data tables within each switch on a per port and possibly per VLAN basis. So these are stored in tables like this per port, like this 1, 2, 3, or for VLAN if your layer 2 are configured as a virtual LAN. As an example, after each switch has learned the location of every station, these databases would contain the information shown in Figure 3.9. So switch A's database, switch B database. After of course, it needs to turn on first, and over time, after some flooding, it will be able to save that port into its switch data table. So here, filtering databases on switch A and B from figure 3.8 are created over time, learned by observing the source address on frames seen on switch port. When switch bridge is first turned on, its database is empty, so it does not know the location of any station except itself. Whenever it receives a frame destined for a station other than itself, so not including its port of course, it makes a copy for each of the ports other than the one on which the frame arrived, and sends a copy of the frame out of each one. So basically, if it doesn't know it yet, it will send the frame to a network. It is possible. Then if the network responded that yes, it's me, it will save that in its database, so that it won't need to send frames to all of the network element. If switches, bridges never learn the location of stations, every frame would be delivered across every network segment, leading to unwanted overhead. The learning capability reduces overhead significantly, and it is a standard feature of switches and bridges. Today, most operating systems support the capability to bridge between network interfaces, meaning that a standard computer with multiple interfaces can be used as a bridge. In Windows, for example, interfaces may be bridged together by navigating to the network connections menu from the control panel, highlighting the interfaces to the bridge. So here, we can actually bridge multiple network. Right-clicking the mouse and selecting bridge connection. So when we click right-click here, it will actually bridge connection. So when this is done, it will pop up a control that allows us to bridge connection. When this is done, a new icon appears that represents the bridging function itself. So a new icon will represent the bridging function. So most of the normal network properties associated with the interface are gone and instead appear on the bridge device or on the new icon that you can later configure, right? So all of the properties of the individual interface will be gone because it is now configured as a bridge or switch. So in Windows, the bridge device is created by highlighting the network interfaces to be bridged, right-clicking and selecting the Bridge Network Interfaces function. Once the bridge is established, further modifications are made to the bridge device. Figure 3.10 shows the properties panels for the network bridge virtual device on Windows 7. The bridge device properties include a list of the underlying devices being bridged and the set of services running on the bridge, like the Microsoft Networks client, file, and printer sharing. So here in figure 3.10, it actually shows the properties panel for network bridge virtual device on Windows 7. The bridge device properties include a list of the underlying devices being bridged and the set of services running on the bridge. So these are the devices being bridged and the set of services running on the bridge, which is at the top. Sorry, these are the services, the cost, package, scheduler, file, and sharing, and these are the one being bridged, the local area connection and wireless network connection. So you can see this is the configure button we are talking about. So Linux work in similar way, but instead using a command line arguments. So in this this command line argument produces this kind of network topology. The part 2 is, or the ETH1 is the Linux, where the Linux stands, or how it is located in this network topology. In this simple topology, a Linux-based PC is configured to operate as a bridge between the two Ethernet segments it interconnects. As a learning bridge, it accumulates tables of which port should be used to reach the various other systems on the extended LAN. As a learning bridge, it accumulates table of which port should be used to reach various systems on the extended LAN. So since we extend this LAN, this Linux PC is where we store that table that learns where various other systems can be reached on this extended LAN. And here's the command line for that. The simple network of figure 3.11 uses a Linux-based PC with two Ethernet ports as a bridge. So these are the two Ethernet ports, the 1 and 2. Attached to port 2 is a single station, and the rest of the network is attached to port 1. So as you can see, Linux, like switch, has multiple ports. The following commands enable this bridge. brctl add br0, brctl add if br0 eth0. So this is the eth0 is this is the eth1, and the br0 is this, the Linux itself, kind of like the master and slaves. ifconfig eth0 up, ifconfig eth1 up, and ifconfig br0 up. So again, brctl add br0, brctl add if br0 eth0, brctl add if br0 eth1, ifconfig eth0 up, ifconfig eth1 up, ifconfig br0 up. The series of commands creates a bridge device br0 and adds the interface eth0 and eth1 to the bridge. So the br0 is actually what makes the bridge. Interfaces can be removed using the brctl del if command. Once the interfaces are established, the brctl show max command can be used to inspect the filter database, called forwarding database, or FDBS, in Linux. So that's actually called a forwarding database. So here, brctl del if actually can be used to remove the interface. The brctl show max command can be used to inspect this database. So here, brctl show bridge name, bridge ID, br0880. So brctl show max br0. The output of this command reveals one other details about bridges. Because stations move around, have their network cards replaced, have their MAC address changed, or other things. So it's normal for a PC or station. For laptop, it's not normal to change network card, but for PC, before, it's actually normal, or it's not normal for PC to get down. So they're designed to have a timer like this. So once the bridge discovers that a MAC address is reachable via a certain port, this information cannot be assumed to be correct forever. That's why they have that timer. So to deal with this issue, each time an address is learned, a timer is started, commonly defaulted to 5 minutes. In Linux, a fixed amount of time associated with the bridge is applied to each learn entry. So each learned entry here has time, usually 5 minutes. If the address in the entry is not seen again within the specified aging time, the entry is removed. So it's automatic in this database as indicated here. As you can see, we set that to 1 second and we remove some of the MAC address. So as you can see, we can also see if it's local here. The port, we can see the port number, MAC address is local, aging timer. So here we have set the aging number value unusually low for demonstration purposes. When an entry is removed because of aging, subsequent frames for the removed destination are once again sent out every port except the receiving one, called flooding, and the entry is placed anew to the filtering database. The use of filtering database and learning is really a performance optimization if the tables are empty. The network experiences more overhead but still functions. So, what are the flooding? Let's make it clear. The situation. A bridge is a software switch which has a MAC address table. It maps which MAC address lives on which port. So a bridge is actually just a software switch. So example, MAC address 00AABBCCDD01 port ETH0, then MAC address 00AABBCCDD02 port ETH1. So if a frame arrives for 00AABBCCDD02, the bridge knows send that only to port ETH1. So if a frame arrives to this, the bridge will say send that only to this. Or the bridge knows send that only to ETH1 instead of ETH0. If that is what the current table means. But what if it doesn't know where the MAC is? So that's where flooding happens. Flooding means the bridge sends that frame out every port except that one it came in on. So it's kind of like multicast except the one it came in on. It's like saying I don't know which port has 00AABBCCDD05. So just shout it out to everyone. Whoever recognize it will respond. So example, step by step. Let's say host A, MAC AA on port 1, host B, MAC BB on port 2, host C, MAC CC on port 3. Bridge MAC table after aging is empty. Host A, so bridge MAC table after aging will be empty. For example, let's start with an empty table. Host A wants to send an IP packet to host B. At layer 2, host A wraps the IP packet in an Ethernet frame. Destination MAC BB colon BB, source MAC AA colon AA, payload IP packet TCP data. So the bridge VR0 receives it on port 1. So at layer 2, basically the host A wraps the IP packet in an Ethernet frame if it wants to send to host B. So the source is AA colon AA and the source destination MAC is BB. Now the bridge check its table. Do I know where BB colon BB is? No, it has age out since we started with empty table. So the bridge floods that frame. Sends a copy to port 2 and port 3. So it actually sends frame to port 2 and port 3 but not back to port 1 to avoid loops. So the result, host B MAC BB colon BB says, hey, that's me, accepts it. Host C sees it's not addressed to CC colon CC and drops it. At the same time, the bridge learns, oh, BB colon BB just replied from port 2. So I will add now that to my table. Next time I'll send it directly to port 2. No more flooding needed. So here host A is the visual diagram for port 1. Connected to bridge, which has the MAC table, which is connected to port 2 and port 3. So frame from A plus B, unknown MAC, flooded to all ports P2, P3. Next frame to B, sent only to P2, learned. So how this fits in TCP or IP? Sorry. So here the frames from A to B are actually sent not just from B, because it doesn't know it yet. It is sent to B, to port 2 and port 3, or to B and C. But the next frame to B sent only to P2 because it has learned that in its table. So how this fits in TCP or IP? So let's zoom up the stack. So layer 4 protocol TCP, what's happening? Connection between two IPs. L3 or layer 3 protocol IP packet has SRC IP colon 192.168.1.10. The DST IP is 192.168.1.20. So L2 Ethernet. So Ethernet frame has SRC MAC AA colon AA, DST MAC BB colon BB. So in physical, bits over wire or Wi-Fi. When you send a TCP packet to another IP in the same subnet, your OS wraps it in an Ethernet frame destined for the peer's MAC address. If the bridge doesn't yet know where the MAC lives, it floods the frame, letting the real destination receive it and respond. Once learned, future TCP or IP packets move along the correct path layer 2. So in Linux, when you saw this earlier, BRCTL set aging BR01, you told the Linux bridge to forget max after 1 second. That means flooding will happen frequently because the bridge keeps forgetting where devices are. Normally, this would be 300 seconds, so flooding happens rarely. So output explained. So per port 1, this or the MAC address, is it local? No. Aging timer 0.76, meaning bridge learn this MAC from frames on port 1. It's about to age out, 0.76 left. Port number 2, this is the MAC address. Is it local? Yes. Aging timer 0.00. This MAC belongs to the bridge itself, its own interface. Port number 1, again, with this MAC address. Is it local? Yes. Aging timer 0.00, another local interface, maybe the virtual interface of BR0. So port 2, number 2 with this MAC address, is it local? No. Aging timer 0.78, learned from port 2, not yet age out. Port number 1 with this MAC address, is it local? No. Aging timer 0.00, learn from port 1, just refreshed, saw new frame. So aging and flooding, when a MAC entry ages out, no frame from it for greater than 1 second here. The bridge just deletes it. So no frame greater than 1 second. So next time a frame is sent to that MAC, or the session will be, you can think of this like a session. So the session will be deleted after 1 second if the aging times out at 1. Next time a frame is sent to the MAC, the bridge doesn't know where to send it. So it floods or broadcasts. It's actually broadcast, not multicast. The frame out, all ports except the one it came in on. When that device replies, the bridge relearns the correct port, update its table again. This is how switches learn and forget devices dynamically. How it connects to Ethernet and TCP or IP. Think of the layers. Layer 2, name Ethernet or data link. What happens here? Frame addressed by MAC addresses. How this example fit? BRCTL manages this layer. Aging table decides how frames are forwarded. So the BRCTL are actually manage this layer too. And these frames are addressed by MAC addresses. And aging table decides how frames are forwarded. Layer 3, IP. Packets addressed by IP addresses. So above the bridge, when two VLANs or IP subnet exist, you need routing between them. So if you have two VLAN, again in the previous video, you will need a routing between them. So here's the visualization. Application, browser, ping, etc. TCP or UDP. IP uses IP address 192.168.1. Ethernet or bridge layer uses MAC address 00:17, etc. It learns MACs, ages them out after 1 second, floods unknown destination MACs. When the bridge forget a MAC, the next Ethernet frame from your TCP or IP stack for an IP peer will be flooded until the bridge relearns which port has that MAC. Once learned, subsequent IP packets and thus TCP session go directly to the right port. So again, once learned, subsequent IP packets and thus TCP sessions go directly to the right port. So again, that's where the TCP session is a bridge, using that. It's the same with the messenger. With the previous video, that's how you create that session, because the switch already learned that. It saved that in the database. Connection to IANA. That's also why at the start it's hard to connect, but after that it became easier. So connection to IANA in VLANs. IANA assigns global IP address, layer 3 identifier. The bridge doesn't care about IP, only about MACs, which are layer 2 identifiers. VLAN segment layer 2 domain. So each VLAN has its own separate MAC table and aging process. So each VLAN actually has its separate filtering table, so we will need to configure that differently. A router layer 3 device connects these VLANs using IANA assigned IP subnets. So a router will be able to connect these two VLANs using the IANA assigned subnet. So host A connected to port 1, BR0 Linux bridge MAC table ages 1 connected to port 2 to host B. So layer 2 learns MAC to port mappings, ages them out. If idle, it flood unknown MAC. Layer 3 IP packets from TCP or IP use this MAC underneath. Next, we turn our attention to the case where more than two bridges are interconnected with redundant links. Let me just sip my coffee. In this situation, flooding of frames could lead to a sort of flooding catastrophe with frames looping forever. So what if there's two bridges or more than two bridges are interconnected with redundant links? Bridges may operate in isolation. Spanning tree protocol. So this is actually how we solve this using this protocol. Bridges may operate in isolation or in combination with other bridges. When more than two bridges are in use, or in general when switch ports are cross-connected, the possibility exists for cascading or looping set of frames to be formed. So here, an extended Ethernet network with 4 switches and multiple redundant links. So if you have multiple switches, kind of like the trunks we discussed in the previous video, there's a possibility of redundant links, which kind of like make the switch useless. If simple pole flooding were used in forwarding frames through this network, a catastrophe would occur because of excess multiplying traffic. a salt called broadcast storm. So because of it sends broadcast, it will have this loops or redundant links or frames. This type of situation requires the use of STP protocol. Assume that the switches in figure 3.12 have just been turned on and their filtering devices are empty. When station S sends a frame, switch B replicates the frame on ports 7, 8, and 9. So it replicates the frame to be sent or broadcast to this. So far, the initial frame has been amplified 3 times. So these frames are received by switch A, D, and C. Switch A produces copies of the frames on port 2 and 3. Switch D and C produce copies on ports 20, 22, and 13 and 14 respectively. The amplification factor has grown to 6 with copies of the frames traveling in both directions among switches A, C, and D. So it travels both directions, which produce this redundant frames because those switch then copy the frame or does the broadcast. Once these frames arrive, the forwarding database begins to oscillate as the bridge attempt to figure out which port is really the one which station 5 should be reached. Obviously, this situation is intolerable. If it were allowed to occur, bridges used in such configurations would be useless. Thankfully, STP protocol are invented. So STP works by disabling certain ports at each bridge. So at each switch. So that topological loops are avoided or the redundant links. No duplicate paths between bridges are permitted. Yet the topology is not partitioned. All stations can be reached. So we allowed no duplicate paths or redundant links, but also we didn't partition it. We still allow all stations to be reached. Mathematically, a spanning tree is a collection of all the nodes and some of the edges of a graph such that there is a path or route from any node to any other node spanning the graph. So it's a spanning tree is actually a node, kind of like a node data structure, a graph data structure rather, that has this tree inside it, but there are no loops. The edge set forms a tree. There can be many spanning trees on a graph, so STP finds one of them for the graph formed by bridges. So there can be many spanning trees on this graph. So again, we have multiple trees in this graph, and STP finds one of them for the graph formed by bridges as nodes and links as edges. So STP kind of like this algorithm automatically combine these multiple trees in this forming this graph. So using STP, the BAAC and CD links have become active on the spanning tree. Ports 6, 7, 1, 2, 13, 14, and 20 are in the forwarding state. All other ports are blocked, like not forwarding. These keep frames from looping and avoid broadcast storms. If a configuration change occurs or a switch fails, the blocked ports are changed to the forwarding state and the bridges compute a new spanning tree. So in this figure, the dark lines represents the links in the network selected by STP. For forwarding frames. So in this figure, the dark lines represent the links in this network selected by STP for forwarding frames. So these dark lines are what this algorithm or STP protocol selected so that no one could be duplicated. None of other links are used. Ports A, 8, 9, 12, 21, 22, and 3 are blocked. With STP, the various problems raised earlier do not occur, as frames are created only as the result of another frame arriving. There's no amplification. Furthermore, looping is avoided because there's only one path between any two stations. The spanning tree is formed and maintained by bridges using distributed algorithm running in each bridge. So we need to be able to configure this kind of like in Linux, but it's not BRCTL. We're gonna use the STP protocol that use distributed algorithm running as a bridge. So each bridge should be able to do that because they should be able to avoid the redundant link or form this link depending on the network needs. As with forwarding database, STP must deal with the situation where bridges are turned off and on, interface cards are replaced, or MAC addresses are changed. Clearly, such changes could affect the operation of the spanning tree, so the STP adapts to these changes. So just like the filtering database, it also adapts when the devices are turned on and off. The adaptation is implemented using an exchange of special frames called bridge protocol data units. So it uses a bridge data or this BPDU frame to be able to adopt this whenever some MAC address are removed, which eventually happen in this interconnected or uh, things happen in networks, right? Computer comes and go. The frames are used for forming and maintaining the spanning tree. These frames are used for forming and maintaining the spanning tree. Aside from that distributed algorithm, the tree is grown from a bridge elected by others and known as the root bridge. So it was elected by others known as root bridge. So as mentioned previously, there are many possible spanning trees for a given network. Determining which one might be the best to use for forwarding frames depends on a set of costs that can be associated with each link and location of the root bridge. So there may be many possible spanning trees for a given network. So that the number of spanning trees that you will configure depends on a set of costs associated and the location of the root bridge. Costs are simply integers that are recommended to be inversely proportional to the link speed. So the costs are actually directly proportional to the link speed. For example, a 10 megabytes per second link has a recommended cost of 100. So if it's lower, it has a higher cost, right? And 100 MBS and 1000 MBS links have recommended cost value of 19 and 4 respectively, so they have lower cost. STP operates by computing least cost paths to the bridge using this cost. So this is actually how this algorithm calculate the path to be able to get to that destination host faster using this cost. If multiple links must be traversed, the corresponding cost is simply the sum of the link cost.